A learner wants to set up a standard cell using nickel as one of the electrodes. So what I've done is I've marked nickel over there. To which of the following half cells should the nickel be connected to produce the largest potential difference? Now, one of the things that bothered me about this question is I don't know if you have to go from magnesium to magnesium 2 plus, and from cadmium to cadmium 2 plus, and from copper to silver, and from silver. In which case, the bottom two are negated automatically. Because they are going to be non-spontaneous, because you have to go backwards at the top and forwards at the bottom. And then obviously the next one is the biggest difference over here is definitely in that direction. So at least is definitely with the magnesium, because magnesium is further from the nickel than from the cadmium, than nickel is from cadmium. So what I'm going to do first is I'm going to say I definitely know it's not that. I'm going to pretend that you can just use the half cell. And I also definitely know it's not that. And the reasons I know that is because of the fact that they are closer and therefore will have less of a potential difference from nickel. Okay, so now if we're looking at nickel at negative 0.25, we can now do the calculations where we change the sign of the magnesium because it's going backwards. So it becomes plus 2.37 minus 0.25. And you get 2.12. I'm going to then assume spontaneity on the next one. And I'm going to say, I'm going to change the sign of the nickel now. And I'm going to say plus 0.25. And change this and keep the sign the same of the silver. And that's going to be 0.8 plus 0.80. And very good news is that it turns out that this turns out to be 1.05 volts, which is a lot less than the 2.12 volts. So even if I did it backwards, forwards, or round and about, that one doesn't work. So the biggest potential difference comes from the magnesium over there. Right, then the next thing we want to do is which of the following is a redox reaction? Whenever I'm looking for a redox reaction, the very first thing I do is I go on a little hunt for an element on its own. And I have that. Yay! I've got this copper over here on its own. So it goes from copper 0 to copper 2 plus. That must be a redox reaction. And if I look at all the other reactions, they definitely don't have something on their own. So there's nothing starting at 0. So you'll probably find all the oxidation states will stay the same. So B is your correct answer. Which of the following standard electrode cells would give the highest EMF? Firstly, I do not recommend you do this question. The main reason is that it is going to take you 10 minutes to get 2 marks. When you finish the paper, you come back for this question. But otherwise, you just leave it because it's far too time consuming for 2 marks. Right, I'm going to do it anyway. I have marked the iodine and silver, the magnesium and manganese, the chromium and the copper, and the lead and the mercury. I've done them in colors each time. And it looks to me pretty much like this peachy one, the lead and mercury are furthest apart, so they'd probably give the right answer. But I can't assume that. And in fact, it turns out in this one that it doesn't even work out. So I'm going to start with the iodine, and that's in silver and iodine. So I have to do the iodine goes from iodide, so I have to go backwards on plus 0.54, which means I have to change that sign to negative 0.54, and I keep the positive on the silver at plus 0.80. That turns out to be a very small number. I mean, I think it's 0.3. So that is not looking like a promising candidate for the answer. The next one is the magnesium and manganese, and there I'm going to go backwards on the magnesium, so it's going to become plus 2.37, and I'm going to go forwards on the manganese, which is minus 1.18, and that leaves me with 1.19 volts, which is not a bad potential difference. Then we can try the chromium, and we're going to say, going backwards on the chromium, it's positive 0.74, and then on the copper it's going forwards and it's positive 0.34, and I land up with 1.08. So it's close, it's a good candidate, but it's not winning. It's It's not winning against the other one, so I'm going to cross it out straight away. Oh, and PS, that one obviously has disappeared as well. And then finally, let's look at this mercury and lead, which we thought was possibly the top candidate. So I'm going to go 0, I'm going to change the sign, plus 0,13, and then I'm going to go to mercury here, plus 0,79, and I'll end up with 0,92. And that is also not a good candidate. So the correct answer there is your magnesium one, B. What is the most consistently reliable salt to use in a salt bridge of an electrochemical cell? You now need to think about solubility rules, and the minute you've got silver chloride, by the way, the chlorides of silver and bromides and iodides are insoluble. Calcium carbonate, the carbonates of calcium are insoluble. The sulfates of copper are not bad, but the sulfates of everything else are a problem. So to use it in your salt bridge is a bad idea. So potassium nitrate, and I said that to you. I said it in the video, that potassium nitrate is a universal, excellent salt bridge substance. Why? Because all potassium salts are soluble and all nitrate salts are soluble. Determine the EMF of silver and magnesium electrode, electrochemical cell. So let's try and spot those two. We first have to find the silver. Good news, we found it. And the magnesium we've also found over here. And now if they're spontaneous, we change the sign of the magnesium. The magnesium goes backwards, the silver goes forward. So it's going to be plus 2,37. Keep the sign the same, 0,80 for the one that goes forwards. And you get a fabulous answer of positive 3,17. What is the appropriate solution to use in a calcium half cell? Calcium sulfate is insoluble, calcium phosphate is insoluble, calcium carbonate is insoluble. Look for the nitrate. The nitrate's always